Good morning. Today's lecture is all about AI and machine learning, and we are going to go into considerable detail today about many of the more advanced techniques in this space. And I'm going to try to avoid a lot of hype and marketing jargon. We're going to go pretty deep into specific methods and techniques. So, learning objectives today, you're going to understand how machine learning actually works without the hype. You're going to be exposed to a variety of contemporary ML methods, and I'm going to provide a number of use cases. Many of those are going to be in medicine. You're going to learn the unique vocabulary of ML, and it really does have its own unique set of terms. And then you'll see how ML techniques can be applied to real-world problems. And I'm actually going to be showing you some Python code here today as well, because many of the principles will appear to be somewhat abstract. And I think in showing you some Python code, you'll actually see how you can go about implementing these techniques. And I hope finally that you'll be inspired to stand up an ML team, an effort to build out some solutions. So I will be providing a brief introduction to machine learning today, and then I'll get into specific styles of machine learning: supervised learning, unsupervised learning, and then I'll spend the bulk of my time on more advanced techniques, artificial neural networks and deep reinforcement learning. These are the methods I'm going to cover in the lecture today. We'll go through supervised learning techniques, which I consider to be more traditional data analytics techniques, unsupervised learning, and I'll focus on data dimensionality reduction. And then finally, again, the bulk of my time I want to spend on artificial neural networks and more advanced topics. During the course of the lecture, I'll provide many examples in medicine. These are the ones that you will see highlighted. I'll also touch on some autonomous driving examples and some other potential use cases. A little bit about my background. I'm currently doing some R&D with a startup I've launched called Locomi. That's focused on AI in medicine. I also have my own advisory practice. I advise clients like Qualcomm and others in the tech space. And then you can see I've worked for a variety of tech companies as well as in academic medicine. This is the gap that I want to address in the lecture today. I think there's a big gap in terms of the adoption of more advanced techniques that are coming out of the research community, and I don't see those being adopted in the corporate world. And that's going to be my focus today, really focusing on more advanced techniques, hoping that the corporate world will start to invest in some R&D in the space. So the audience here, if you are a expert in data science and machine learning, this lecture is really not well suited for you. If you're a business executive, a corporate leader, doing M&A work, venture capital, this lecture is really focused on you and getting you up to speed on many of these techniques. The gap I was talking about is expressed here. I say at best in the corporate world, we have only about 5% of corporations in the aggregate are really even doing any work in the advanced ML techniques. Most of what I see is with traditional algorithms, and I'll touch on those in the supervised learning section. And we see a pervasive number of products coming out in the market that are really hyped up as having some AI capability, when in fact they're basically doing old-style statistical regression. And so we do have this definite gap, and I really think that the corporate world could benefit and gain some competitive advantage by leveraging some of the more advanced techniques we'll talk about here today. So let me get into an introduction to machine learning, but then I promise you I'm going to go pretty deep into many of these techniques. In the enterprise space, we've had various trends over the last few years, like a mobile-first strategy, big data analytics, Internet of Things, and now I think we've got a big shift into an AI-first strategy. And those forward-thinking organizations that start to embrace AI as a competitive advantage, I think, are going to have a leg up. Now, for example, at Apple, Tim Cook recently said the mother of all AI projects is the car project. Well, I've spent considerable time looking at autonomous driving and comparing it to my own domain of medicine. And I think the application of AI and machine learning in medicine is about 5 to 10 times more complex than autonomous driving. And I think you'll see that by way of many of the examples I'll talk about here today. Now, AI has been around a long time, and machine learning is a subset of AI, and deep learning is a subset of machine learning. And I'm going to touch on today machine learning and deep learning in pretty good detail. Now, I also have indicated there, so that was my on-ramp there, knowledge-based systems. That's where I got my start in the early days in AI, and that's where we tried to encode an expert's domain knowledge into the system. And those were mostly knowledge-based systems, expert systems, and those techniques have fallen by the wayside. This is me back in the day with an experimental system at University of Michigan. This was a moderately unsuccessful attempt at encoding human intelligence into a system, a knowledge-based system. What we're going to be seeing today is very different. The more modern approaches, when we talk about deep reinforcement learning, for example, we're going to establish a framework by which we can train on, but we're going to avoid hard coding any rules in the system, and you'll see how that works. Now let's start off with the idea behind machine learning, and then we'll get into some detail. So the basic idea is that humans can learn from experience, and so can machines. Machine learning is the art and science of designing computer algorithms that learn from data. So we're going to get away from traditional deterministic programming, and we're going to focus on establishing computer algorithms and artificial networks that can learn from data. You'll see when I show you code, we're basically establishing a framework and are going to avoid hard coding a lot of rules in the system. So why is machine learning finally starting to take off? Well, I think that model performance is starting to dramatically increase, and the advanced methods we're going to discuss have proven some good results here. In the more advanced techniques, you need a lot of compute performance, and I think we're, of course, on a steady trajectory with regard to that, and the amount of data that many industries have made available has dramatically increased. And without the availability of data, we can't do any training on algorithms. And the red bar is what we want to be mindful of, and that is to what degree we can ultimately achieve or exceed human performance. Now, traditional algorithms have only gotten us so far. Many of these are what I'll call in the world of big data analytics and data mining. Most of those you'll find in the corporate world and what I'll call more traditional approaches. It is the larger neural networks, artificial neural networks with many, many layers that are getting more complex that have really shown some great promise here. Now, we've seen really a ramp up. And back in the day when I was doing the early work in knowledge-based systems, we had a little ramp up in investment, but that fell by the wayside. Here now we have a good steady ramp up of investment in the space and companies that are establishing venture arms dedicated to AI investments. And I see these really ramping up over time as well. And of course, now we have a nice landscape of companies that are being invested in. And I think given the amount of money that's pumped into this space, we're only going to see this number of companies increase. And this is good news in the corporate world. You could start to partner with these emerging companies and leverage them for competitive advantage. All right, now let's start to go a little deeper now into how this stuff works. Traditional deterministic software engineering, conventional programming is illustrated there at a very high level. And in the corporate world, you're very good at estimating cost and schedule now with regard to traditional programming activities. You encode rules to meet various business objectives, test it out, and deploy it. Machine learning is a little bit different in that we are going to get away from hard coding rules in a system. You're going to focus on training algorithms, either in unique combinations of different styles of algorithms together with other approaches. And you're going to be training on data and really rely on the algorithms to do the heavy lifting for you. So it's a very different approach than deterministic programming. Machine learning is a bit more experimental and scientific. In more advanced work, you'll see in the examples I'll provide, it's very much sort of a scientific discovery approach and a very much trial and error, if you will, as opposed to pure engineering. Machine learning is more complex because it's open-ended. In many of the more breakthrough projects, you're going in without really an understanding of what might work. You're throwing a lot of different techniques at a problem, and you're doing a lot of trial and error. There's more tuning, if you will, than debugging of code here. Now, the tools in this space are different than one might be accustomed to in the corporate world. And if you're going to ramp up this capability, you'll need to start to look at a mix of tools. Now, we're in the early days here, and I think these tools are going to evolve over time, and we're going to see some new entrants as well. But these are tools that most corporations are not currently using. Now, for somebody like me who's a Python guy, you'll see in a number of examples I'll provide, I'll be leaning on a number of these libraries in some of the code examples. Now, Python, for example, may not be a language that many corporations are even using. So it requires a bit of a mind shift, if you will, in terms of the adoption of new languages and new tools. Also, we have now dedicated hardware. In the last few years, I think we've lost sight of hardware. It's been somewhat commoditized. But now we see a resurgence in dedicated purpose-built hardware designed for machine learning and artificial intelligence. And I envision more progressive organizations establishing a high-performance computing group that understands how to tune this hardware that will work side by side with the machine learning experts. I think we're just in the early days of that. And software development methodologies as well. You may have in your organization traditional software development methodologies. You'll need to rethink that in terms of now the process for developing machine learning and what a process might look like. This is just one example at a very high level of starting to think about what a methodology might look like. This other one is perhaps more granular. It's a three-step process. The first step is all about data. And if you are an organization that has not proactively invested in an enterprise data warehouse, then you are going to be a step behind. You're going to spend a lot of time pre-processing data and scrubbing data, which is a big upfront piece of work in any machine learning project. If you already have that data made available to your machine learning team, you have a leg up. And you can see there's a lot of that pre-processing, scrubbing, preparation of data to get it ready for training. And then generally what you do is you split it out into training, validation, and test sets. And then the work of applying various algorithms and tuning those models, and then testing that out and doing a lot of iteration there. And of course, validating, deploying that capability. There is a lot of math behind what we're going to talk about today. And what I find in the executive leadership ranks of companies, chief information officers, digital officers, and the like, if you've had advanced math, you've probably long since forgotten that. And we're going to go through this just to give you an idea of what is behind the techniques that we will discuss in more detail here. There is a lot of calculus. So, for example, uses a method for finding minima and maxima. When we talk about optimization of artificial neural networks, I'll introduce some ideas around finding the minima in order to improve the training cycle for artificial neural networks. Integral calculus is used for probabilistic modeling. And then linear algebra, I think, is the math of the future with regard to this space. a lot of manipulation of matrices using dot products, vector spaces and norms, convex, non-convex solutions, projections, and then eigenproblems and singular value decomposition for reducing data dimensionality. And we'll spend some time on some techniques there. Now, what do the equations actually look like? I've got a few slides that just give you an idea of some of the math. Now, during the course of the lecture, I am not going to break apart the notation. While I'll introduce many of these topics, and I'll give you examples, I may express some of those in Python code, but we're not going to go into the notation in great detail. I'm going to abstract that out here. But I just want to make you aware of what some of the math looks like behind the methods here. We'll spend some time talking about backpropagation, which is an important component in artificial neural networks. Many of these techniques we'll cover, okay? All right. How are machine learning models selected? A lot of it is going to be based on the experience of the team that you hire and whether they have encountered a similar problem in the past. But you've got to recognize there's a lot of experimentation and trial and error. So while you might be pretty good today at estimating cost and schedule with regard to deterministic programming, here this is going to be a lot tougher to do. It's very open-ended, a lot of trial and error, and you're going to see many of the solutions that you arrive at. You'll try to achieve a good balance in what we call good generalization. And that's represented here on this slide. So we have the overfitting problem here, which is you could be working with an algorithm and feeding data into it, and it looks like it's doing a good job in terms of training on your data. But when you bring a new data set in, the model falls apart. It's learned the intricacies of that initial data set and does not have good generalization. The other end of it is underfitting, and that is where you don't even have the right model that you're working with for the data, or you're not tuning hyperparameters properly. It's the balanced approach, and this applies to all of the methods we're going to cover here today, where you're tuning a system to achieve good generalization and that can learn against a variety of data. Now, the first step that goes into a machine learning project is feature selection. And that's what's observable that you can use to train various techniques. And this is all about being very smart about selecting out the right data that will achieve the highest performance for your models. And I'll give you an example in medicine, for example, here. If we have some predictions we'd like to make around patients with congestive heart failure, we could select out those elements here that are most impactful for our training model. Here, we'll feature select off of this database, which is a tumor database, and I'm going to be showing you this database in a number of examples here today. It's been publicly available for a number of years. And many people have done testing against it. It's basically a pathologist's impression of whether a tumor is malignant or benign based on the attributes of that tumor. And you can see a number of items there. And again, to be very smart about those items, those elements that you'll feature select out that'll feed into algorithms that will give you the best performance. Now, I am going to touch on today three major styles of machine learning: supervised learning, unsupervised learning, and artificial neural networks and reinforcement learning networks. Again, the bulk of my time will be focused on more advanced artificial neural networks, but I am going to run through pretty quickly supervised and unsupervised learning. All right, so let's start with supervised learning. This is what I'll call the more traditional approach you see in many companies doing data analytics work. There are basically two types of supervised learning problems. One is classification and the other is regression. Now, with classification, we're going to output a category, and regression, we're going to output a scalar value. And I'll show you most of the examples today, I think, will be in classification. And I find that that's where most of the work in the corporate environment is focused right now. Now, in supervised learning, we deal with what's called labeled data. And so the data is going to be recognized by the machine coming in, and then we have an expected outcome or output, maybe a scalar value or a classification. This is a typical workflow for supervised learning, again, bringing data in, selecting it off, and then splitting it out into training, validation, and testing, and then applying various machine learning models and techniques and tuning those to achieve a good validation. So let me run through now very quickly a number of supervised learning techniques, and these are the major ones, and these can perform quite well, albeit for more traditional work. So the first one is the easiest one to understand, and that's the decision tree classifier. It makes predictions based upon segregation of subgroups, and here I've listed various algorithms that are available to you to do that. So what you will do is you'll pump information into a decision tree classifier, and it will segregate data out and classify it. And then when you bring new data in, that data will automatically be segregated according to where the algorithm believes it falls into the tree. I've also included an example there in medicine and immunology, which can be a pretty complex topic, and I'll refer to this later in a more advanced example in artificial neural networks. So many of these, while I have information on one slide, we could do an entire lecture on each technique. So I'm giving you several semesters of information here in trying to consolidate it in terms of just one lecture. So I'm going to run through pretty quickly here. You have these slides. You can refer to it in more detail later. So the next one is random forest. It's nothing more than a collection of those decision trees, and each tree gets a vote in classifying, and you can average outputs. It can be quite powerful and can do a number of things for you there. A similar approach is ensemble learning, only that the models don't all have to be decision trees. This can be a variety of techniques that we're talking about here in supervised learning. And the average outputs of each classifier using bagging, boosting, or stacking techniques can be quite powerful. The intuition here behind ensemble learning is that you could have three relatively weak methods, and the aggregate output of each could give you something that is quite powerful. All right, K nearest neighbors compares a new data point with other data points by finding the distance between them. So here's an example here that I've worked up. So the tumor data set we referred to earlier, we're going to feature select off some items there, some data elements, and I have available to me in K nearest neighbors one of three distance functions, and in this example we'll use the Euclidean function. And I've included some Python code there so you can see how you would start to work that up in code. I'm calling on NumPy, which is a math library, and Pandas, which is very good for reducing data dimensionality and scrubbing data. And you can see I'm abstracting out the math. I'm calling a classifier that will do the heavy lifting for me, and we might produce a graph that looks something like that. Now, while I'm showing you a lot of graphic output here today, that may not be your final objective. It's just a way for me to express how these algorithms work against data. Support vector machines. SVMs use a scoring function to draw a hyperplane that's called a decision boundary. And we're going to create a gutter, if you will, between data that may appear to be quite close together. But we're going to bifurcate that data using this technique. I've included a lot of information there on that slide that you can refer to later about the stepwise method for doing that calculation. Naive Bayes has been around a long time. It's based on the Bayes theorem. Naive implies that all data is addressed independently by the algorithm. Actually, it's a collection of algorithms. Again, here I've included a lot of detail that you can refer to later, and a very simple example of how you might use this in medicine, where you refer to some historical trends in a table, and then bringing new data in, you can make a comparison and a prediction. Logistic regression has been around a long time, and we will refer to this when we talk about artificial neural networks as well later, and we talk about activation. But here in this example, I'm trying to derive a dichotomous output. Again, the tumor data set, I'm going to feature select off x sub 1, x sub 2, and x sub 3 with a bias vector and some weights into what looks like a sigmoid function. And then a logistic regression, you can see what it's doing there. It's going to output a 0 or a 1. So while all this data may appear to be quite close together, logistic regression is going to try to get all the data into a value of a 0 or a 1. Now you can see in the Python code, again, I've abstracted out a lot of math. At the bottom left is what you might produce. So you might be able to classify based on the attributes of a tumor whether you believe that tumor is malignant or benign. That's a dichotomous output. You could also do multi-class as well with this. So how is this used in more advanced techniques as well? You're, I'm sure, familiar with the IBM Jeopardy game, the deep QA architecture that they built to play that game. Basically, if you look at it in a nutshell, what they put together, they have a method for selecting out the right Jeopardy response. They're taking in information from the game. They're breaking that text out in natural language programming. They're comparing that against a huge database, and they're coming up with a candidate list of responses that they would provide back to the game. And in down selecting the appropriate candidate, they use logistic regression. They tried a number of supervised learning techniques we've discussed here, but logistic regression tended to work quite well, and they used that in the final iteration. All right, that's enough of supervised learning, the more traditional techniques. Now we'll talk about unsupervised learning. So while supervised learning deals with an expected input, a labeled input, and an expected output, conversely, unsupervised learning deals with unlabeled inputs and, in some cases, unexpected outputs. That is, we may have highly complex multidimensional data, and we want to draw some correlations and associations to see what we can pull out from that data. One common technique here is called k-means, and this is where we're going to cluster data together, and I've included the equation there. In this example, you can see we have highly complex genetic data, almost 1,400 expression values of informative genes for colon cancer. It's a way to start to, through this complex information, start to unlock and uncover some patterns in data. Which brings me to the topic of multidimensional space reduction, or data dimensionality reduction. In many unsupervised learning problems, like the one we just discussed, you'll have very, very complex data, and you may need to do some data dimensionality reduction on that data before you start to apply it into an artificial neural network or other techniques. And I'm going to run through here three types, methods that are commonly used for reducing data dimensionality. The first one is called principal components analysis. Now here's a case where what I have on one slide we could do a lecture or two on. The math behind PCA based on eigenproblems and singular value decomposition would require a lecture just to go through the math here. So I've abstracted that out for you, and I've given you another example of some RNA sequencing data, again, very complex data, and applying a three-step process in general is what singular value decomposition does against this data, and you may produce something like the map at the bottom. So again, trying to draw some correlations and associations there that you can start to work with. The other approach is called t-SNE, and again, it's a technique for reducing the dimensionality of data where you're going to take data and then project it on a 2D plane. and there's a perplexity hyperparameter that you can adjust, and I show you how that parameter works on data there. Now, comparing PCA to t-SNE, illustrated here against two styles of sequencing, RNA and ATAC, you can see that they have a different effect, and there's no hard and fast rule in terms of what's better than the other. It's a lot of experimentation in terms of your particular use case. The last technique I'll mention, if you have a lot of asynchronous time series data, like video data or data from sensors that is coming in, and you want to train on that data and you want to reduce its dimensionality, core sets is a great approach for that. This is an example here of a group that's videotaping laparoscopic procedures and then trying to do intelligent segmentation of that video for training using core sets as a reduction technique. Okay, so that's supervised and unsupervised learning and data dimensionality reduction. Now we are going to get into where all of the excitement is in deep learning. This is where the academic community is spending considerable time, companies like Google and Facebook and Amazon doing a lot of research with many of these techniques. This is the area that I don't see the corporate world really ramping up yet in terms of leveraging these techniques, okay? But we're going to run through these. And again, these are the most powerful techniques right now. I will provide you with an introduction to artificial neural networks, and then we will get into specific types of networks where you'll see many of the general principles applied in real-world problems. So I'm going to start at a very, very high level now and talk about the general attributes of artificial neural networks. So very simply, artificial neural networks are functions for transforming input arrays into output arrays. And to perform this mapping, neural networks stack layers of computation. Each layer consists of neurons and a linear function followed by a nonlinear transformation. And an important component here is backpropagation that optimizes the performance of the network by adjusting the weights, for example, with gradient descent. And we'll talk about what that is, and we'll go through various styles of that. And the goal of backprop is to compute the partial derivatives of the cost function. Now, artificial neural networks have been around a long time, but it wasn't until the notion of backprop, where we could improve learning through adjusting weights and biases in the network, that we really took us to the next level. Now, I want to give some credit to a professor here at UC San Diego who, with his co-author, basically invented backprop while he was here in 1986. He wrote a book where he introduced the notion of backprop, and this was a very important piece of work that we still use today, and it's a foundation for training artificial neural networks. Now, as the name implies, artificial networks are inspired by biological networks, and we won't spend a lot of time getting into the biological networks and what they're comprised of. I've included some bullet points there that you can refer to. I'm sure you know that the biological networks and neurons have a synapse that can get fired through an electrical impulse, and you can fire a neuron and activate it by that impulse. On the artificial neuron side, what we have done is tried in math to replicate many of those techniques, if you will, that are naturally found in biology. So the artificial neuron is reflected there. We have inputs, weights, summation, and then the very important activation function, and we'll talk about various activation techniques that are available to you to determine whether, in fact, you want to fire a neuron. Now, what we're seeing is the trend right now, anyway, is toward larger and larger neural networks. The complexity is dramatically increased. Many neurons, many activation functions, many layers of complexity. And here's a representative column of the neocortex. We're starting to see similarities now with very complex artificial neural networks. We'll be talking about some of those examples here. All right, so very simply at a very high level, abstracting out quite a bit here, I'm going to start at a high level of an architecture for an artificial neural network. So we always have in yellow the input layer, and then in light blue is represented what we call hidden layers, and then we have an output layer. And we're going to understand how well the algorithm is working by calculating a loss or a cost function, and we'll talk about techniques for doing that here in a moment. And then we're going to optimize through, again, backpropagation, weights and biases in the network, and we'll talk about methods for optimization here as well. And that's how we go about improving the training of an artificial neural network in general. All right, so let's get into some of the techniques here in a bit more detail and what's available to you for training. So, activation functions. Introduce nonlinearity in a network to learn more complex patterns. Complex networks use different activations across layers. You're going to see in very complex networks a variety of different methods for activation, and what I've done is I've ranked them here in general by performance. There's 3 flavors of exponential linear units, and then a hyperbolic tangent, which looks sigmoid, and a logistic regression that should look familiar to you from supervised learning. Okay? You will see these when we go through examples of artificial neural networks, how we're using these for various activation functions in the network. Optimization through backpropagation. Now there's a lot on this slide, and I left it that way so you could refer to it later. Okay, there's a lot of information here and a lot of detail if you want to go through the equations. I've also included some Python code as an example of how you would express that in code, trying to abstract out some of the math. But this is how you're going to increase training efficiency by finding the highest accuracy and the minimum error by minimizing the cost function. This is where we're going to be updating weights and biases in the various layers of the network. Now, there are 2 major techniques for optimization. The first one is called gradient descent, which increases training efficiency by finding the highest accuracy and minimum error. And what we're trying to do is find the minima, and then control the variance and then update the model's parameters, leading ultimately to convergence. And there's 3 styles of gradient descent: batch, mini-batch, and stochastic. Batch is considered the least efficient. So if I have 1,000,000 pieces of data that I need to calculate at each step in terms of finding the minima, I calculate all of those 1,000,000 points at each step toward the minima, which can be quite inefficient. Mini-batch is more efficient in that we can establish a parameter. Say I only want to take 10 data points and calculate those at each step. And then stochastic, as the name implies, brings in some randomness. And a common theme that you'll see across many of these techniques is when you bring some randomness in, it actually improves the learning process. We'll talk about an example of that when we talk about deep reinforcement learning. Atom is another technique that is quite powerful, and it's one that many people have been trying lately and throwing it at a problem initially. It's very simple to tune, very high performance, only has 4 hyperparameters, alpha, beta 1 and 2, and then epsilon. Very easy to use out of the gate and has shown some good results. Okay, so those are the general principles of what an artificial neural network is all about. It contains neurons that can get activated. We have input layers, hidden layers, output layers. We have activation functions, as well as through backpropagation, we have optimization techniques. Now, how are those actually put into practice? So now I'll start to introduce specific styles of artificial neural networks. And you will start to see how these techniques are expressed in different ways here. So the first one is what's called a convolutional neural network. And again, with this one, I will start at a very high level, abstracting out a lot of the underlying details, but then we'll get pretty specific here. So convolutional neural networks are very good for imaging and vision problems. So in this very high-level example expressed here, we want to do facial recognition. So I have a couple million images of people's faces, and I'm going to train on those through this network. And then I'll pump in someone else's, a new person's face, and I'll attempt to do a prediction. Okay, at a very super high level right now, sort of general principles of this, okay? Now the first layer of a convolutional neural network is the input layer. That, in this case, we're inputting the raw pixels of the image. And the first layer of a convolution is where we break that image down into pixels. And we use what's called a patch or a receptive field, and I'll show you this in code, how we define that, to establish how much of that image we're going to pull out, how many pixels, what is the depth, and how we're going to move that in a window-like fashion across the image. Moving that window across the image and collecting those pixels is called a stride. And we'll have various layers of activation, various layers of convolution, where we'll start to build the image back up, where ultimately at the end, in what we call a fully connected layer at the output, is where we'll do a scoring. We'll make a prediction about who it is we're looking at in terms of this, this image, okay? Now this is very good for autonomous driving. If we have a camera at the front of a car and we're doing autonomous driving, it's probably pretty good to recognize, you know, that that's a stop sign versus a yield sign, for example. Those sort of use cases are sort of low-hanging fruit, if you will. So then they are multi-layered networks for solving computer vision tasks. The purpose of a convolution is to extract features from the input image. We're going to set small squares up as inputs, either as we call them a patch or receptive field. We'll define that in software. And then when we move that across the image in a window fashion, that's called a stride. And the typical layers of a convolutional neural network, we always have an input layer. In this case, we're inputting the raw pixels. The convolution layer computes the output of neurons connected to the local input regions, computing a dot product between the weights in a small region of the connected input volume. And then you'll see activation functions that we referred to earlier. A variety of those activation functions. And then a pooling layer does a downsampling. And then again, the fully connected layer is always at the end. Okay, so what does that actually, how does it look like in a real network? So here's an example that I've worked up. So here's a convolutional neural network for detecting brain anomalies from MRI images. So the idea here is that I have a couple 100,000 MRI images of the brain. I have images that represent a variety of conditions, everything from Lyme disease to Alzheimer's to a tumor in the brain. I also have images of completely healthy brains as well. And I'm going to go about training a convolutional neural network here using the layers that I describe here. We have various layers of convolution where we're pulling that image apart. And then we have rectified linear unit there as an activation function. And then another convolution layer, another activation, and then a pooling layer does a downsampling. Now we could have many, many layers like this, depending on what it is you're trying to achieve. And ultimately at the end is the fully connected layer where we're doing some prediction. Now I am using as the basis for this architecture the TensorFlow inception architecture, okay, as a starting point. So we do that training and we get good predictive results. And now we'll put that into practice. So we have a 55-year-old male with vision problems, headache, and numbness. And we suspect based on those symptoms that he may have a tumor in the brain. So we do an MRI image, and again, we run it through this convolutional network, breaking the image down into discrete pixels in a patch, and over successive layers, we're going to make a prediction. And at the end, very fortunate for him, there are no issues that we found. Okay, so that is a very sort of high-level example of how you would use a convolution network for medical imaging. Now, I've introduced a lot of abstract concepts of optimization, backprop, activation, various layers I've expressed here. How do you actually go about implementing that? What I've done is just provided for you, and you can refer to this in more, you've got more time later to refer to this. This is some Python code that I've put together here. It is not a complete example, but just to show you how you would express those abstract concepts in code. So we're calling a NumPy library. This is using Google's TensorFlow tool. Now what I'm doing is I'm going to start building up convolutional layers. So you can see it's different than deterministic programming. I'm establishing the architecture of the network. What do the layers look like? Here I'm assigning a pixel patch size. I'm making a determination about what activation function I'm going to use for the first layer. And now we're building up the second layer. And I haven't included all the code here for all the layers, but just to give you an example of what it looks like here. Various other functions. And then here is where we're loading in the brain images. And then we're starting to train the model. Okay? There's a lot more code, obviously, that goes into this, but I just want to show you that. Sometimes when I get into showing, abstract concepts, it's hard to translate that into what you might actually implement in the real world, okay? Now, the next example is the evaluation of 12-lead electrocardiogram image segments by convolutional neural network. So you're, I'm sure, familiar with a 12-lead electrocardiogram. That's those strips. These are patches that are put on patients. You measure the electrical signals from the heart, and based on the measurement of those signals, they're represented as waveforms on a strip. And the idea here is that I want to do training on the segments of the waveforms represented on those strips, both for patients that are completely healthy with a normal sinus rhythm, as well as patients that express abnormal waveforms and those segments. Now, as you can imagine with this problem, there's a lot of pre-processing involved in terms of breaking the segments apart to get them ready for training. Okay, 12 lead is the gold standard that you'll find in a hospital. Many of the consumer-oriented devices are 1 lead. Okay, so this is really the gold standard. Now, in years past, the way you would approach something like this, if you want to do some machine learning, you probably would use one of the supervised learning techniques we talked about earlier. And you would look at the scalar values being expressed by the electrical signals. And taking those numbers and doing some machine learning on those values. This is a different approach in that I'm actually going to use the waveform images and use a convolutional neural network as a classifier. Okay? So we do training on several thousand of these healthy waveforms, those with various abnormalities. And now we have a 41-year-old patient that presents to the emergency room with intermittent chest pain. And we do a 12-lead ECG, and we run it through our trained convolutional neural network, and you can see that we're breaking the image down in a very discrete fashion in a patch, and then moving those image segments up in terms of scaling, where ultimately at the end, we're going to make a prediction. And in green is what the outputted prediction is. Now, any cardiologist would look at that output and tell you there are some problems there. And what we do with this patient is we take him to the cath lab and find that he does indeed have a clogged artery, and we unclog the artery and put a stent in. Okay? Now, the same inception architecture that I just used for the 2 previous examples has been used by this group at Stanford, for example. Same style of network only in dermatology. So we have skin lesions we're training on, and we make a prediction at the fully connected layer of whether we believe that skin lesion is malignant or benign, for example. Here's good work, similar network actually, by the team at Google. So diabetic retinopathy. We have images of the eye, both healthy images as well as eyes that represent some form of diabetic retinopathy. And we go through that same process of convolution and activation and pooling, where ultimately then we can predict whether a patient has diabetic retinopathy or just has a healthy eye. And good work, similar network, actually the same network, the Inception network, out of Germany here, images of the mouth and detecting whether there's incidence of oral cancer. Now, in those examples, we all relied upon a common architecture, and that is an example of transfer learning. And the idea behind transfer learning is that, let's say we have a very good football player, he's good at blocking and tackling and passing. Chances are his skills can be transferred quite readily into the game of rugby, right? This is the same sort of example where the Inception model that was developed at Google was initially trained on images in the wild, and we've applied that with good results in medicine. Now, hopefully we're going to see more of those opportunities because the development of a convolutional neural network like the Inception model is non-trivial, and it's painstaking work by many people on a team, and I think many corporations don't have those resources today. So if you can leverage transfer learning opportunities, that might give you a leg up. All right. Now we're going to talk about, this is an exciting area. It's gotten a lot of attention lately. A lot of breakthroughs here in generative adversarial networks, okay? GANs. Now, these are based on what we call a two-player minimax game. And taking the principles from a two-player minimax game and applying it to artificial neural networks, where we're going to have two artificial neural networks that basically compete with each other. Now, in many use cases, these models can learn to create data that is similar to data that we give them. And the objective then is to understand and explain the underlying structure of the input data even when there are no labels, so in an unsupervised learning fashion. Okay, so a lot of people, their initial work here using GANs has been on images, and I'll show you some examples of that. But then I'll show you an example I've worked up where I'm leveraging some of these techniques in combination with other techniques where we're looking at metadata. So let's start off with the more traditional use cases here. So it's a two-player minimax game. We have two artificial neural networks competing against each other. The first network we call the generator. And in this use case, the generator is the forger, the counterfeiter. Its job is to look at the attributes of a real image and try to replicate that and synthesize that. And it's going to start creating a lot of images, okay? Its job is to generate and synthetically generate images. That's one network. The other competing network, remember two-player minimax, the second player is the discriminator network, and its job is to look at the images coming out of the generator and to determine whether it believes those images are real or fake. And this is all done in mathematics. Now, this is a typical maximum likelihood problem. And traditionally, you would use an explicit density function, where if x is the input vector, the distribution of data concentration measures the log probability of a density function. But here in GANs, we're using an implicit density function. So if the input vector has a high probability of being real, then the discriminator assigns a value of 1. So if you get a value of 1, those are keepers, if you will. They're very accurate in terms of their attributes. So a 0.5, for example, would be an image that you would throw out. Okay? It doesn't really match the original very well. Okay then, so again, formally describes a learning process using two-player minimax game. J superscript D is the cost function of the discriminator, which is the cross-entropy cost associated with a binary classification problem. The process compares a single mini batch from sample data and fake data from the generator, and the cost for the generator is the negation of the cost for the discriminator. Now that's the general principle behind it. You can do some interesting vector space computation. Okay? These are some examples. So I can start to synthetically generate images using vector space arithmetic, for example. Okay? A man with glasses minus a man plus a woman. Now, what I have done is turn my attention to medicine and applied this in a bit of a different way. Now, most of the examples we have seen thus far have been on what I'll call more low resolution images. Now, in medicine, we deal with super high resolution. So there's some tweaking that has to be done with these techniques. And I won't get into all of the detail, but here's one I've worked up where I have an MRI image, and then I have a positron emission tomography image, and in silico, I can synthetically generate a PET MRI hybrid using a two-player minimax game technique with the equation that's there. And that's all the detail I'm going to provide here with that, okay? All right. Now, let me talk about a technique that I've worked up that I call exploitative GAN. All right. This is where I'm going to look at the attributes of data, of molecular data, cellular data, very complex data, not image data, but I'm applying some of these techniques along with a variety of other techniques in the mix. And in more advanced work, you're going to find that you're bringing together a variety of different advanced techniques in a unique combination to achieve a result. And this is certainly one example of that. All right, so the hypothesis here is, and I will describe what these are in more detail here, but the hypothesis is that an exploitative GAN can uncover natural killer group 2D receptors for use by CAR T cell therapy in solid tumors. So let me go through and give you a little bit of a primer in terms of what some of this terminology means, okay? We have two ways I'm going to talk about here of killing cancer. The first is innate to your own immune system, and those are natural killer cells. They go to work every day. They kill cancer cells as well as viruses, and they're activated by binding to the antibody attached to a cell, displaying a peptide antigen through what we call MHC1. Okay? Best to just show you an animation here of how this works. So that is a cancer cell, and we see antigens being expressed on its surface. In white, we'll see the natural killer cell. And it's going to bind using a receptor. And when it does, it's going to penetrate the cancer cell wall and deliver its payload. And its payload is designed to cause apoptosis, which is the destruction of that cancer cell. All right? Very high level sort of description of how that mechanism of action works. Okay? So that's what is the innate technique that we all have. Now, many pharmaceutical companies are investigating something called CAR T. And this involves removing white blood cells called T cells from patients and introducing a new gene into the T cells that enables them to recognize the cancer. After the gene is transferred and expressed, the T cells are then infused back into the patient where hopefully they start to attack the cancer. And that process looks like this. So you can see it's quite similar, and again, hopefully causing the destruction of the cancer cell. Now, these techniques to date have not worked well. CAR T techniques have not worked well for solid tumors. But we know that natural killer cell receptors and those mechanisms of actions do work. So using a variety of techniques, can one start to discover maybe approaches where you could start to combine some of what's available to us from NK in terms of receptors and start to think about applying those expressed as ligands for CAR T use. And without getting into a lot of the detail, there's a lot here on this slide, but this is really what I call an exploitative GAN. So the decision tree we talked about earlier that I discussed in supervised learning, we're going to extend that tree and start to break out activating receptors there. Now, when we define those receptors, it's quite complex data, so we'll probably use t-SNE as a data dimensionality reduction technique. And then you'll see there a list of receptors that are expressed through an NK process, group 2D receptors. And now we've got an expression of ligands there on the bottom right, and then above that, we now can start to identify solid tumors that could be addressed by natural killer cell receptors for CAR T. So can CAR T start to exploit natural killer cell receptors? And there's a way of simulating all of this, again, in silico using some of the techniques of a GAN, but there's a lot of other techniques in the mix that I won't really talk about here today, okay? All right, this is a good time for a break, and then when we get back, we'll talk about recurrent neural networks, one-shot learning, and then we'll spend the last bit of time talking about the good work that Google has done in the DeepMind team in deep reinforcement learning, which is a very exciting topic, okay? Okay, welcome back from break. We're now going to talk about recurrent neural networks. And these can be quite powerful for a number of use cases where you have time series data, sequential data coming from sensors, for example. And they're very good at recognizing patterns and sequences of data. They're called recurrent because they perform the same task for every element of a sequence, with the output being dependent on the previous computations, and they have a memory which you can interrogate. So this is one style of recurrent neural network, LSTM, long short-term memory. You'll see this used in a number of powerful examples, and you may find this useful in your work if you're dealing again with data that's flowing in real time, for example. And you see that the general construct illustrated here has a number of activation functions where you can open and close various gates. And those should look familiar to you from our activation function discussion. And then we have a cell that you can interrogate using a peephole function. You could start to think about expanding these, and I'll show you an example of a team that's expanded a traditional LSTM and bolted on a nice add-on here. Okay, so how are these used? Well, in autonomous driving, for example, we have a number of sensors. Now, certainly the camera information we can deal with a convolutional neural network, right? Those are obviously very good for dealing with vision. But we have a lot of other sensors. We have LiDAR and many others here. And all of this information is flowing in real time. So it would seem that an LSTM would be a natural style of network to deal with that. Time series data we can train on to figure out, driving patterns and then be able to adjust dynamically, right? Okay. Well, it turns out that the overall architecture is quite good but doesn't scale well enough for real-time autonomous driving. And this group that was funded by Bosch Automotive did some good work in this regard. You'll see where they've bolted on a time gate. And that time gate can deal very well with buffering information coming from the sensors. And this is just an example. When you're doing more advanced work, you may start off trying a very basic technique, and then you may need to innovate and add on specialized capabilities to meet your use case. The other one is a sequence-to-sequence LSTM, very good for something like an intelligent chatbot, illustrated here, or for language translation, for example. Okay, so here's an example where we're combining different techniques we've covered here thus far. And again, remember my takeaway here is that in more advanced work, you're going to be combining different techniques together in novel ways. So here we want to see whether we can do machine annotation of X-ray images. Well, if we're dealing with X-rays, then those are images, so there must be a convolutional neural network in the mix, perhaps, for dealing with the X-ray inputs, as well as maybe some other networks like a recurrent neural network for dealing with text and annotation. And this is the example here on the left block, and this is really abstracted out a lot of detail, but you can see the unique combination of convolutional neural network as well as a couple recurrent neural networks in the mix. Also, dimensionality reduction technique we referred to earlier, TSNE, is in the mix as well. All those in a unique combination. There's other techniques I'm not going to address here that all brought together quite a compelling solution. Again, a lot of experimentation, a lot of trial and error, but with good results. You see in light green is the machine annotation of the X-ray, and the true annotation is represented in yellow. So combining techniques together in novel ways can get you some great results there, okay? Self-organizing maps. These are purpose-built artificial neural networks, purpose-built for data dimensionality reduction. Very unique design in that they have no hidden layers. And you can throw a lot of complex data at these and break that data out and represent it quite simply. And the example that I'm going to cite here is related to molecular subtyping of bladder cancer using self-organizing maps. So we want to predict the survival rates of patients with bladder cancer from this molecular biology data, and we want to represent it in a way that a practicing physician can really easily understand. So as you can see, we have highly complex data there, and through a self-organizing map, you can get something like that you can distribute to a physician to help them understand survival rates. All right. One-shot learning. Now, this is an emerging area. I just wanted to expose it to you, get you thinking about this if you have some use cases that require this. Here's the idea between one-shot learning. Humans can learn new concepts with very little supervision. A child looking at a picture book can select out a bird very quickly and learn that that's a bird with very few samples. Now, we know from the examples we went through here today that many of these networks require many training samples to learn on. But what if I'm in a domain and I don't have a lot of training samples? Well, then I need to architect some artificial neural networks that can deal with few samples, and that's the architecture around one-shot. Now, here's a group that is doing drug discovery, targets of potential drug discovery targets using a one-shot learning technique and a design of a specialized artificial neural network architecture that helps them do that. So in this example, they don't have a lot of samples they can train on. They can attempt to architect a network that would operate on a limited number of samples. All right. Now, this is the final block of material, and it's where a lot of the excitement is here in deep reinforcement learning. Now, what I'm going to do is talk about the principles of reinforcement learning, the general principles, the foundational aspects of it, and then I will get into some specific examples from the Google DeepMind team. Okay, so let's first start off by some of the theoretical underpinnings, if you will. This is a general reinforcement model. Now we have an environment. The environment is the world in which we're operating in. It could be this auditorium, it could be a factory floor, any environment that we want to do some training in. The agent is going to figure out what actions we should take in that environment. And we're going to always be in a current state and think about moving into the next state, taking an action to evolve into the next state within the environment and within the physical constraints of an environment. And when we take a good action, we receive a positive reward. And if we take a bad action, then we're penalized. So a very high level sort of concept around reinforcement learning. Okay? This is based on what's called a Markov decision process. Now, an MDP, the basis for an MDP is that only the current state matters. So I have no history about how I got to where I'm at right now in my current state. I'm only concerned about what the next best action is I need to take to move into the next state. And I'm going to figure out what the best action is that I need to take. And when I take a good action, I'm reinforced by a good policy, a good reward. Now, a Markov decision process is illustrated here. So I'm just giving you sort of the foundational principles that are behind some of these networks we'll talk about, okay? So we define an MDP with states, transitions, actions, and rewards. States are always represented as S. That's where we are at now in the environment. Transition is the probability that you'll end up in S prime. S prime is the new state, given that you took an action and ended up in a new state. And actions are always represented as A. Those are things that are available to do in the environment. And the reward, again, is a value for taking a good action or a penalty for taking a bad action. Now, the solution you derive is a policy, always represented as pi S, takes in a state and returns an action, and the optimal policy is always expressed as pi star, which actions we favor in a given situation. So let's start to think about how to translate some of these principles and express them in various styles of artificial neural networks. So if we're thinking about now machine learning, it's going to be an area of machine learning concerned with learning how an agent should act in an environment so as to maximize cumulative reward. We have agents that observe current state and take an action based on its observation, and the policy is very important. It's going to tell us what the good actions are versus the bad actions. And the environment is often a simulator where we can start to apply these techniques and learn to get better and better over time through a simulator. Now, there are two basic ways of deriving a policy. There's what I'll call a good enough policy with no refinement. You get to a certain level, and that's about it. You're going to stop getting better, if you will. Value learning is about getting continuously better over time through rewards. And this is where on the bottom of the right slide there, the right side of the slide, we're going to find Q state action pairs, Q values. We'll talk about that in more detail, but Q value learning is a key component of the networks we're going to talk about. Now, a good policy should strike a balance between exploitation and exploration. Exploitation is about referring to, for example, a Q table that will inform what the best potential actions might be in a given state. But exploration is a little randomness. Now, if all you do is exploitation, we found that artificial neural networks kind of get stuck, if you will. You need to bring in a little stochasticity in the process, a little randomness to try some things out once in a while and start to inform your rewards using random actions. You get better results. So in deep reinforcement learning, always be mindful that greed is good. And the notion of a little greediness, what we call e-greedy exploration, is something that has shown very good results. That is to bring in a little bit of randomness, and we can set a parameter for that. So for example, if epsilon is 0, that is fully exploitative. I'm only relying on what I think is a good next action. If I do a 0.05, for example, that brings in a little bit of randomness in the process. Okay? All right. Now we're going to talk about, I mentioned the Q value, the importance of that, and that is the basis for deep Q networks and deep Q learning. Now, we could spend 2 or 3 lectures just on the next few slides here. So I'm going to cover this at a very high level to expose you to this. Just recognize that better actions have higher Q values. And we're going to maintain Q value state action pairs in what we call a Q table that you can refer to. We also have something called the credit assignment problem. Which of the preceding actions was responsible for getting the reward and to what extent? That's important to know, how we got our policy reward. Also, what this informs us is it helps to answer this very, very important question. What are the expected long-term rewards given a certain state that we take a certain action, that we do every subsequent action perfectly? Now, in a traditional form, we talked about an MDP, we talked about the basic principles now. The application of those in a general sense do not scale all that well, okay? But there's ways we're going to talk about addressing that problem. Now, here's a very important equation that I provided to you that is the foundation for deep Q learning and deep Q networks. Again, I won't go through a discussion of the notation, but you do have notes there that you can refer to. This is based on something called the Bellman equation. And I've also provided you some pseudocode, and then at the bottom you've got a stepwise description of what that code does. You'll see the equation there, okay? So those are the foundational principles of deep reinforcement learning, of deep Q learning. And now how do you take all of those principles and to start to think about constructing an artificial neural network that can start to learn on those principles? And that is what a deep Q network is. A network that takes you from a state to the Q value of each of the actions at that state. All right, now we're going to get into an example here. This is good work done by the Google team, the DeepMind team. And this is their diagram. So they had a number of ideas around MDP, around some of the ideas we just talked about, those principles, and applying those. Now, the first thing you want to do is try to find a simulator. And so they thought, well, you know, what's available? And they found an Atari 2600 simulator. And there's various games like Breakout that you can play against. And then in their diagram, the brain is the agent. Right, that is going to tell us what the appropriate action is we need to take, that we should take in that game. And actions are expressed obviously in a game, in this game, by the joystick. And then the console there, the game console, is the environment, the world in which we're operating in. And then it's a video game. So all we have as input are pixels. So reflecting back to our discussion about convolutional neural networks, we could probably expect if the only input we have are pixels, then maybe we need some layers of convolution to understand where we're at in that game as well. So what they did is they took many of their principles and built out a network that looks like this. Now this is at a very, very high level. And there are papers available that they publish if you want to dig down into great detail about many of the techniques here that I'm not even going to address. There's a lot involved here. But at a high level, what you see is that we have basically, we're approximating the Q function as a neural network. This is so-called approximate Q learning, which is much more efficient than sort of the generic style of Q learning and Q tables we discussed earlier. The convolution layers are similar to what we discussed earlier in convolutional neural networks. But in a sense, what we're doing in the end is learning a reward policy from the inputted pixels. And they have something called experience replay. The agent builds a data set of experience and then takes random samples from that data set. So they are a little greedy, if you will. And actually, what they did is they actually set a parameter of a 0.05. So a little bit of random exploration really helped here in terms of learning. The outputs are Q values, and there are as many output nodes as possible joystick actions. Okay? Now, there's a lot more that obviously goes into this, but very good results. So again, very different than the work I did in the early days in knowledge-based systems, where we tried to take a domain expert's knowledge and code that in a system. Here what we're doing is establishing a learning framework, and then we're going to start off really dumb. And this framework is going to enable us to get really smart and become an expert on its own. So through this process of getting rewards and policy, we're going to learn the game, or the machine rather, is going to learn how to play the game on its own, if you will. So here's a little example of that. So we start off very dumb, okay? And again, we have a little bit of randomness, so we're going to take some random actions initially, and we're going to learn from that. We're going to get policies now and develop an optimal policy. And we're going to learn to get better and better. At 120 minutes, we actually get pretty good. And then at 240 minutes, what starts to happen is, again, through this reward policy and some randomness and using experience replay, because experience replay now is getting better and better, at 240 minutes, we're getting really good. And we actually understand a strategy now. So in a breakout game, one strategy is you want to break out, for example, on the left side and then attack the wall from the back. And that's what it does. So it learns to become a true expert, starting off with no knowledge at all, just a learning framework. And that is the basis for deep Q learning. Okay. Now, they didn't rest on their laurels, and the takeaway for you is while you may have developed a breakthrough capability, you want to continuously innovate. And that's what they did here. They developed something called asynchronous advantage actor critic. I won't get into all the detail, but it's a viable alternative to experience replay, and it leverages multi-threading and CPUs. There's more detail here if you want to look into it, and there's papers that are published, and you can delve into that. Okay? Now, there are shortcomings to DQNs. So when the Google team published their papers, everybody got very excited. There's sort of a resurgence, if you will, in reinforcement learning now. But when you come out with this work, then people start to think of it as a Swiss Army knife, and you start to try to throw everything at these techniques. And there are shortcomings you want to be mindful of. First of all, if it's a non-MDP problem, that is, remember, Markov decision problem implies that only the current state matters. But if I need to maintain some history, then these techniques out of the box don't work very well. And if you have a long time horizon problem, so Atari is very tactical. There's immediate rewards coming in. If it's a very strategic situation, like chess or the game of Go, which is very complex with strategic moves and delayed rewards, then you need to change things up a little bit from the original architecture. And then it's simulator dependent. As we saw in that example, they had a benefit of an Atari simulator that you could iterate on and get better and better over time. If you don't have a simulator, either you need to invent one or think about bolting on some other capabilities. So on the non-MDP problem, if you need to incorporate prior actions, you may want to think about one style of network we discussed earlier, which is the recurrent neural network, LSTM. Remember, it has some memory capability, and combining an LSTM with deep QN might give you at least an initial framework that you can play with. If you have a long time horizon problem with strategic moves and delayed rewards, maybe you want to start thinking about developing a search tree that predicts Q values, for example. So this is work after the Atari challenge. The Google team took on the game of Go. And they built a system called AlphaGo that took many of these principles to see whether they could apply it to the Go game. Now again, this is a little different. It's a slower moving game, very strategic, a huge playing surface, and just a huge number of potential moves and delayed rewards. And what they built out actually has shown good results, and they beat the world champion, Lee Sedol. Now, this is an example of, again, more advanced work and combining different techniques together. And what they did is they reached back to something that was available in the 1940s called Monte Carlo tree search. And they combined that with a DQN, and then there's a lot of other techniques that we won't get into in detail here. But that unique combination of leveraging an old style technique like Monte Carlo with newer techniques has really proven out to be quite effective. And so combining those, they're estimating the future rewards for a particular action and then prioritizing search based upon a guess of future rewards, and that worked quite well. It looks like that at a high level. Monte Carlo always has 4 steps: selection, expansion, evaluation, and backup. There's some notes I've included there, and there's a bunch of papers available if you want to really dig into this. But it's a great example of being very creative, where you've got a breakthrough technique like DQN, and then you're trying to address the shortcomings of it, and you reach back into something that was available from the 40s, like Monte Carlo. All right, now we will wrap up with a quick run through of these topics. So when in the corporate environment, you're going to stand up a team to do machine learning and deep learning, and you're going to, as an organization, innovate on your own models, and maybe that'll be some secret sauce that you'll develop for competitive advantage. And then also I would encourage you to have a scouting function where you're always looking at what's coming out of the academic world and publicly available techniques. That combination of techniques is what we call a model zoo, and you're going to maintain that model zoo and iterate on that. You'll then maintain a leaderboard where you will rank various techniques that you have that have proven to address various problems, okay? Now, you're going to be measuring the performance of your learning models using a number of techniques. And this is one that I just want to expose you to that you'll see that's available: receiver operating characteristic graphs. You'll see results like this. And not that this topic is confusing enough, but you'll see confusion matrix, where you'll look at number of true negatives, true positives, false negatives, false positives. Ways of looking at the performance of what you're doing, okay, in different, using these different techniques. Finally, a validation. So remember we talked about good generalization, avoiding overfitting or underfitting, getting good balance and tuned solutions. Cross-validation is a method for ensuring that you can train equally as well on different data. And there's various techniques like K-fold, hold out, leave out, and those 3 that are mentioned here that you should be mindful of. In this example, let's see, that's 1, 2, 3, 5. That's a 5-fold. We would call this a 5-fold cross-validation technique, so that I'm separating my data out, my training data, into 5 different subsets, and I'm making sure that my techniques can learn equally well on all 5. Okay, finally, I will leave you with this: the promise of AutoML. And there's a lot of research going on here. The idea is that could you have a neural network that would train a neural network? In the corporate world, this would be really an advantage. We did talk about transfer learning as an opportunity, but here these would be tools that you could start with, that you would input a number of ideas around what you're trying to achieve, and it would generate a very complex artificial neural network. If this comes to fruition, that would be great news because building these very advanced multi-layered networks is non-trivial and really a huge task, okay? So that concludes today's lecture. I hope I've inspired you to invest in AI, machine learning in your organizations, and you go forward and build a number of creative solutions. So thank you.